to section 6.1. Today we're going to start talking about the dot product, or sometimes it's called the inner product. And let me give you a brief overview of where we're going with this. As we know, not all linear systems are consistent. The example I have here is of an inconsistent linear system. Col A is spanned by the single vector 1, 2, because the second column of A is simply a multiple of the first column. But at the same time, Col A is the set of all B such that AX equals B for some X. Well, if B is over here, not lying on the line spanned by 1, 2, then AX equals B has no solution. However, can we find an X such that if we have to stay on this line, we can still be as close as possible to the vector B? And the answer is yes, and that would be called a least squares solution, and those are used in statistics quite a bit. So I'm going to let you read through these kind of interesting applications of dot product to your grocery items and ISBNs of books, and I'm just going to jump right down here to the new definition of dot. So taking the dot product hasn't changed. We're just looking at it in a slightly different light. We're using this definition of U dot V is U transpose times V. So we're thinking of the dot product as matrix multiplication. Now, in reality, that's not going to change the way you dot. So for example, in this problem here, U dot V is still going to be 18 plus 2 minus 15, which is 5. But let me just show you how that would go with the new definition. U dot V is U transpose times V. Think of U as a 3 by 1 matrix. So U transpose would be a 1 by 3, 3, negative 1, negative 5. And we're multiplying by the matrix 6, negative 2, 3. So our answer will be a 1 by 1 matrix, which we're going to think of as a number. Our answer again is the same thing. It's going to be 5. And you can think of that either as a 1 by 1 matrix or a number. Okay, so when we think of the dot product like this, one advantage we have is we can apply properties of matrix multiplication to properties of dot to prove certain properties. And so I'll let you read through those proofs on your own. And let's just jump down to, this is a long section, so I want to go through it fairly quickly so you're not here forever. The definitions of length and unit vector. So the length of a vector is the square root of V dot V. Now this generalizes the notion of absolute value. The absolute value of A is the square root of A times A. And what this is the distance from A to the origin. Okay, and a unit vector is a vector whose length is 1. So a couple things we're going to be using fairly often. If you want to get rid of the square root in this formula, you can just write that formula as the length of V squared is V dot V. And typically we'll want to find a unit vector in the direction of V. So just take V and divide out by its length, and you will have what you want. So let's do an example. Let's find the length of V for this vector here. So length of V is square root of 12 over 3 quantity squared plus negative 5 over 3 quantity squared, which is the square root of 144 over 9 plus 25 over 9, which is the square root of 169 over 9, which is 13 over 3. And so geometrically what we've done, this point is down here. Let me draw the coordinates, 12 thirds, negative 5 thirds. Think of V as that arrow, and we've just computed the distance from this point to the origin, and that's the length of V. Okay, now let's use that to find a unit vector in the direction of V. So we want V over the length of V. Now the length of V is a fraction, so rather than dividing by 13 over 3, I'll just multiply by 3 over 13, and then multiply by V, 12 thirds, negative 5 thirds, and that gives us 12 over 13, negative 5 over 13. And you can check that really is a vector of length 1. Find the length of this vector and you'll see it has length 1. Okay, distance and orthogonality. The distance between two vectors U and V is the length of their difference. So if we take the length of their difference, that's the square root of U minus V dot U minus V. And I've got a picture over here that can illustrate what that looks like. If U and V are in standard position, we can visualize U minus V as a as that red arrow going from the end of one vector to the end of the other vector. And so the distance between them is just the distance between those 2 points. An important definition is U and V are orthogonal if U dot V is 0. So that's a super important definition. And then just an interest here, we've got a generalization of the Pythagorean theorem that says U and V are orthogonal if and only if the length of U plus V squared is equal to the length of U squared plus the length of V squared. And I just took a stock picture from your textbook to illustrate that theorem. And I believe I put a proof of that at the end. All right, so find the distance between U and V. So first of all, we need U minus V. That's going to be 4 minus negative 4, which is 8. And then 2 minus 3, which is negative 1. And so the length of U minus V is simply the square root of 64 plus negative 1 squared is positive 1. So that's the square root of 65. And then determine if U and V are orthogonal. So we'll use the definition. We want to know what the dot product is, if it's 0 or not. So U dot V is negative 12 minus 6 plus 0. That's negative 18. That's not 0. So no, those vectors are not orthogonal since U dot V is not equal to 0. Okay, now this is a review from section 4.6, and we're going to refer to this in the next few sections, so I just wanted to put it here for your easy reference, because we're going to be talking about row space, column space, and null space actually in the next page. All right, so now that we're done with the definitions, the fun part starts. Suppose you have W, and that's a subspace of Rn. A single vector is orthogonal to that subspace if it's orthogonal to every vector in that subspace. And then we call the set of all of those vectors, the set of all vectors orthogonal to a subspace W, that's called W Perp. It's the orthogonal complement of W. And in English, it's the set of all vectors in Rn orthogonal to W. And in math, it's the set of all x in Rn such that x dot W is 0 for all W in W. And remember, x dot W equals 0 is the test for being orthogonal. All right, so there are two important propositions. One, W Perp is a subspace of Rn. It's not just a subset, it's a subspace. And two, checking to see if a vector is orthogonal to W could be an exhausting prospect because W has infinitely many vectors in it. But this proposition says that a vector x is in W Perp if and only if it's orthogonal to every vector in a spanning set of W. So for example, if W were spanned by two vectors, we would only have to check that x dot v1 is 0 and x dot v2 is 0. So let's do a couple of examples. The first one, if W is the span of this single vector, describe W Perp. So W is a subspace of R3. So W Perp is the set of all vectors in R3, I'll call it x, y, z, in R3, such that that vector x, y, z dot 6, negative 2, 3 is equal to 0. Since W is spanned by a single vector, I only need to check dotting against that one vector. And so I can further clarify that. That's the set of all x, y, z in R3, such that 6x minus 2y plus 3z is 0. Well, that's the equation of a plane. And that plane is orthogonal to the line spanned by that single vector. Okay, let's do a slightly more involved example. Here I've got W, which is spanned by two vectors in R4. Find a basis for W and W Perp. So a basis for W is easy. W is spanned by two vectors, but those vectors are not multiples of each other, so they're linearly independent. So by definition, a basis for W is just V1 and V2. Basis for W Perp. So we want all the vectors in R4 such that they dot to 0 with both V1 and V2. So if they dot to 0 with both V1 and V2, I get two equations. You can check those. And so a way to find the basis for W Perp is we could find a basis for null A, where A is equal to the coefficient matrix of that linear system. So 1, 0, negative 1, negative 1, and 0, 1, negative 1, 1. All right, we know how to find a basis for null A. So I take A and I augment it with 0. and I reduce. There'll actually be nothing to reduce. 1, 0, negative 1, negative 1, 0, 1, negative 1, 1, augmented with 0, 0. It's already in reduced echelon, so I start at the bottom. X4 is free, I'll call that T. X3 is free, call that S. X2 would be S minus T, and X1 is S plus T. So a basis for W perp would be two vectors. I'll write the S vector first, so that will be 1, 1, 1, 0. And then the vector corresponding to the variable T is 1, negative 1, 0, 1. Okay, I'm going to finish up with a super interesting application of orthogonal complements. Recall if A is M by N, A is a map from Rn to Rm. And over here in Rn, we had null A and row A. Those are subspaces of Rn. And over in Rm, subspaces were col A and null A transpose. And this theorem up here says that those aren't just random subspaces, they're orthogonal complements. So for example, over in Rn, row A perp is null A, meaning every vector in row A is orthogonal to every vector in null A. And the same thing happens over in Rm. Every vector in col A is orthogonal to every vector in null A transpose. And I'm going to show you with an example. A is a 2 by 3 matrix here, so think of A as a mapping from R3 to R2. Null A and row A live in R3. Find a basis for null A. So I took A augmented with 0, and you can double check that when you get your basis vectors, there'll be 0, 1, 0, and 1, 0, 1. Okay, those are two linearly independent vectors in R3, so they span a plane in R3. You can visualize that plane is that green plane there, so that would be null A. Now, find a basis for row A. Recall how to do that. We take A and we reduce it down to echelon form B, and in that case, I'm up here, we get 1, 0, negative 1, 0, 0, 0. Take the non-zero rows of B. So a basis for row A would be just that single row vector, 1, 0, negative 1. Geometrically, that spans a line in R3. So this would be row A. Now, section 6 proves that if you take any vector in null A, it is indeed orthogonal to any vector in row A. Those are perpendicular subspaces. All right, the same thing's going to happen over in R2. Col A and null A transpose are subspaces of R2, and we're going to see that they're actually orthogonal subspaces. So a basis for col A, remember how that works. You reduce A to echelon form, and then you take the columns of A that correspond to the columns of the reduced matrix. And so I've got one pivot column here, and so a basis for col A will be the first column of A, which was 1, 2. Geometrically, that's a line in R2. That would be that red line, col A. And a basis for null A transpose takes a little bit of computation. I took A transpose, augmented with 0, and reduced. And so I'm going to get a single basis vector, and that will be negative 2, 1. Geometrically, that's another line in R2. That would be that red line, null A transpose. And those two lines are orthogonal. And that is the end of this section.